Okay, so welcome everybody to the talk about the load balancing library itself, which will include the methods Godehard presented in the previous talk. And so let's just start with that. So a short overview about the talk. I will talk shortly about the philosophy of the design of the library before I continue with discussing the different methods we provide to the user with the library, and then some strategies how to call the library and some additional information about the library. In the end, I will give a short conclusion what is already included in the library and what we are planning to include into the library in the future. So just as a short reminder about what we define as work. The work for us in this talk will be a scalar parameter that describes a workload on a single domain in a parallel application. This might be the execution time of a single routine or a collection of different routines, for example, the routines to compute interactions or to communicate particle data between processes. On the other hand, it might also be the number of particles or the number of interactions or other values that are connected to the work on the different domains. As a basic assumption, we're assuming that this work will be distributed uniformly about or within the volume of the given domain, and that it's distributed according to a uniform work distribution density. So that if we shift an amount of volume from one process to the other, we will shift also a proportional amount of work from one process to the other. So the basic philosophy behind the design of the library were that we wanted to provide an add-on library which a developer can easily add to their code. And this library should provide a suggestion for a better balanced domain decomposition by presenting updated domain borders according to the chosen method. What we do not want to provide, or what we probably cannot provide, is an automatic solution for communication issues that arise therefrom. Because probably all different programs will have different requirements for the calling, different requirements for the communication of particles, because they are stored in different data structures, have different parameters, which are probably not the same for a lot of different codes. And of course, we want to provide different solutions to this load balancing problem, some of which Godehard presented before, and also some others we are currently working on. So currently implemented in the library and tested are the tensor-based, staggered, grid, and histogram-based methods Godehard already talked about. And then there are two methods that work not on rectangular, cubic domains, but on more irregular grids, which we are calling force-based and Voronoi cell-based. The force-based version basically pulls the vertices of the domains into the direction of the most work, and the Voronoi cell-based method does something similar, but is based on the idea that you move around the Voronoi creation points in the direction of the work distribution. Examples how final domain decompositions with the different methods may look are this, for example, this might be the final result of a staggered grid decomposition, while this might be the result of a Voronoi-based decomposition, where the larger red beads represent these creation points that should move to the in the direction of the work, so that the Voronoi cells might or should divide the work better with a better surface to each other than normal rectangular domains. What are now the requirements if you intend to use the library? Your code should, of course, be able to deal with shifting boundaries of domains. This is true for any method you want to use. For some methods, it's also required that you are able, within changing numbers of neighbors. For example, if you use the staggered grid method or the the Voronoi-based method, it might be that from load balancing step to load balancing step, the number of your local neighbors might change. So your code should be able to deal with that. And of course, if you want to use the force-based or Voronoi-based methods, your code should also must also be able to deal with non-orthogonal domains. For example, by using an underlying cell structure, or by being able to determine if particles leave such a domain by doing the geometric calculations. Then there are also some technical requirements. The library itself is written in C++ and Fortran, and therefore you need a compiler that supports at least C++ 11 and Fortran 2003. And if you want to use the more modern MPI F08 module, you even need a compiler that also supports the Fortran 2008 standard. We're using CMake in order to make it easier to build a library, and there you need at least CMake 3.14. Of course, the library is using MPI for its internal communication, therefore you need an MPI compiler. And what we provide as optional features are the output of VTK-based data. There we need at least Virtual Toolkit version 7.1 or newer. And if you want to use the automated documentation creation, you need also Doxygen, Sphinx, and Breeze. In order to use the testing environment, you would need the Boost library. So how would you now include this library to your code? On the left side, we have a really generalized sequence of how a particle or grid-based simulation code usually works. You have a communication step where you transfer data over the boundaries or communicate halos, which might be required in order to be able to compute the interactions in the next step. These might be forces that act between different particles or the solutions of different kinds of differential equations. After you finish these computations of interactions, you usually update your particles or grid positions by updating positions, updating velocities, or updating values on these grid points. And then you continue again with the communication step. Now, if you want to use the library, you would have to add an additional step, which would be to collect the work, either by example, for example, counting particles or grid points, or by measuring time spent in the previous steps to define your work for your program. You would then check if this leads to an imbalanced work distribution. If it does not, you continue your default loop and continue with the communication. If it is in an imbalanced state, you would provide the work you collected to the library. The library then would compute a new geometry and return the suggested geometry to the code so that you could update the geometry of your domain decomposition, communicate the particles then into your into the updated locations together with the usual communication you are doing, and then continue with the normal simulation run. That, of course, begs the question, when should you actually, or how often would you actually call the library? And there are, in principle, two different strategies to do that. Either you're calling the library within a given interval of time steps or after a certain execution time. So that, for example, you have a 100 or 200 time steps after which you will run the library and update the domain geometry, or you would test, for example, after each step, the quality of your load balance in the system, and call the library if it is below some previously defined threshold. These two strategies, of course, have advantages and disadvantages. The advantages of calling the library at regular intervals is that you do not need to check the quality of the load balance in regular intervals, because you just call the library, and this check for the quality of the load balance probably is a global operation, which of course is rather costly. And it provides a defined pattern of calls. So you are sure that every X time steps, the load balancing library is called, and you can see that if you, for example, are taking time measurements. The disadvantage, of course, is if you reached an already well-balanced state of your system, it might lead to unnecessary calls and even unnecessary communication of data if you have small shifts that still would move around particles between domains, although this shift does not really improve the quality of the load balancing in a significant manner. On the other side, the advantages of the triggered execution, triggered library executions, as I call it, would be then that you only call the library if it's really required, because the load balancing quality is worse than your predefined threshold. But this comes as the disadvantage that you need to check the quality of your load balance in regular steps. Meaning you have to perform this global check of the load balancing quality in regular intervals. What you can do to migrate these disadvantages a bit is that you combine these two steps, or these strategies to a certain degree, so that you only check after a certain amount of spent time steps if the load balancing quality degraded to a certain degree, and then would trigger a call to the library or not if the quality is not worse than your defined threshold. What we are currently thinking and working about in order to improve this efficiency of when to call the library is to also provide in the future a function that would suggest if the library should be called, either by performing this global load balancing quality check internally, so that it is not necessary that the user does that, or by using some kind of learning technique where we would take into consideration the previous shifts of boundaries to see if, for example, we are stuck in some kind of oscillating behavior when we are really close to the optimal solution. And what Godard also showed in his talk, we just moved the boundary between two domains in an oscillating manner because we're observing to some kind of discrete length scale, and that leads to this shifting behavior because we're just shifting like 1% of the work, and it's always from like close below half to close above half and again. And that could then also be combined with checking at regular intervals in order to lessen the computational overhead which is required for these triggered calls. So what do we actually get from these calls, or what do we need to provide the library? On the one hand, of course, we need to provide the local work on the local process. And also we need to provide the local boundaries or the local vertices of the local process so that we can do the shift, or that we can compute the new geometry. Another thing we need is the MPI communicator, which also, of course, only needs to be provided once. And if the communicator is not Cartesian, also information about the process grid. So how many processes are there in each direction? The output you would then receive from the library would be the new suggested local boundaries and an updated list of local neighbors if there is an update to be made. For example, if you're using the staggered grid method, and this combined would then be a new suggested domain decomposition for your system. Some other details about the library. As I mentioned before, the library is written in C++ and provides a Fortran interface. It is an open source library, which we are licensed under the BSD3 license. We're using GitLab and GitLab CI features for the development and automated testing. We just released a 0.9 version of the library, which can be found under the given web page. Concerning interfaces to user codes for C++ codes, the library consists of headers, so that no linking of library objects is required. And within the code, the library provides a central class that would take the required parameters that I mentioned before, and would also provide by function calls the new suggested domain boundaries. For Fortran codes, we provide Fortran 2008 based interface that where you either can use derived types or function calls. Optionally, you could also use the MPI F08 module, but then of course you need to use you need to support Fortran 2008. So as a summary, what's the current state of the library? The library currently provides several functions to provide these new domain geometries and topologies if they change, which consists of the new domain boundaries and the new domain vertices, as well as a list of new domain neighbors if the domain neighbors have changed during the load balancing computation. We also provide a possibility to output the domain geometry in the VTK format so that you can visualize it, for example, with ParaView or Visit. We also provide the possibility to maintain a minimum domain size. So, for example, if your system is divided into discrete sublengths, the library would be able to also provide you a system or a domain decomposition where the smallest size of a domain would not be smaller than the provided domain size. For new users and new developers, we also provide small code examples that demonstrate how to use the library and how to add it to a given code. Our planned future developments include that we also include more load balancing more new load balancing methods, for example, methods that are based on bisection strategies. As I mentioned before, we are working on the automized recognition of load balancing quality in order to support users to help them or to help their codes to decide if the library should be called or not. We plan to finish the implementation of the Force and Voronoi-based methods. And then we're working currently on the support on what I call non-strict staggered Cartesian grids. These would be grids that are based on an orthogonal base structure where you have orthogonal domains, but the global grid of domains could not be described as nx times xy times xz nz processes, because you could have a differing number of processes per layer, so that it's not strictly a Cartesian grid anymore. And that's basically what I can tell you about the library for now. And if there are any questions, I would be glad to answer them.
Thanks, René. Well, I have just one comment. The GitLab repo is open, so anybody can click on that and they'll be able to see everything. But the pages, the website with the release, that one is actually behind a login, so just something maybe to fix.
Okay, we'll have a look at that and fix it.